This is the first year algebra-based physics course, and this is topic 2, one-dimensional kinematics. In this section, 2.10, I'll be teaching you how to identify the givens in a physics problem. Another good name for this section would be, how does the real world become a physics problem? Before we start doing actual physics problems, I need to discuss with you a little bit about what physics is and why we're going to be doing so much math, so many math problems in physics. Now, I'll be discussing this for about 4 minutes. If you'd like to jump to the actual problems, then jump ahead about 4 minutes. All right, here we go. Now, physics is the study of how and why matter moves. We usually think of matter as objects, as small as a proton or electron, or as large as an entire galaxy. In this sense, physics is the study of everything in the universe. Now, objects require energy to move. Either an object moves under its own power, or another object causes it to move. As a matter of fact, absolute zero, the coldest temperature possible, that's 0 Kelvin or negative 273 Celsius, is defined as the temperature at which molecules stop vibrating. In other words, they completely stop moving. But the fact that the millions of atoms or molecules in a glass of water or a balloon vibrate faster at higher temperatures and stop vibrating at absolute zero is a little more in the realm of chemistry, or at the very least, in the realm where chemistry and physics overlap. In physics, we look more at the motion of individual objects, again, as small as an electron or as large as an entire galaxy. But in between, we've got meteors hurtling through space, airplanes flying in the sky, clouds drifting across continents, and runners competing in a relay race. Now, don't forget, too, that zero velocity is very, very important in physics and in the real world. For example, we want a bridge, obviously, to have zero velocity. We want the girders and supports to be strong enough not to come tumbling down when we drive across. Zero velocity, otherwise known as static equilibrium, is very important in the construction of bridges and buildings, for example. In this section, we will learn to look at macroscopic objects, big objects, like people, animals, cars, trucks, airplanes, to analyze their motion. We will begin to answer questions like, how fast is the truck going? Well, the truck's going at 30 meters per second. That's a number. How far did the person run? The person ran 120 meters. Again, a number. How long will it take an airplane to get to Istanbul? Maybe it takes 34 hours for the airplane to fly there. Again, a number. Or how quickly will a car accelerate from 0 to a speed of 10 meters per second? All right, perhaps that's an acceleration of 4 meters per second squared. But in any case, you see that all of these questions that we ask in physics involve numbers for answers. What we will do in this section is to learn to translate short stories, problems from real life into physics so that we can select an appropriate mathematical equation to solve the problems in the next section. Every story, every problem or example describes physical quantities which pertain to the object whose motion we are trying to describe. For example, if we want to know how fast a dog is running, maybe we are told how far the dog went and how much time it took. How far is the distance? How long is the time? We know that if we have the distance and the time, if we have the number for the distance and the number for the time, we can use this equation for average speed to calculate the dog's average speed using math. In this section, we will be preparing to use more complicated equations to answer more difficult questions. In order to do well in your physics class, you must be able to give each number in the question a symbol and a name. If we are told that the dog ran 50 meters, we give that physical quantity a name. We call it the distance the dog traveled. If we also know the direction, for example, the dog ran 50 meters north, then we can call it the displacement. We've given the dog's real-life motion a symbol and a name. The displacement d equals 50 meters north. We might also be given the time. The time it took was 10 seconds. In this video, we're going to learn to identify what physical quantities are given in the problem. Physical quantities we will be looking for in this first topic in physics, called kinematics, include the initial velocity, the final velocity, the average velocity, the distance or displacement, the time, and the acceleration. In kinematics, we never worry about the mass of the object or the force that is pushing or pulling the object to make it increase velocity or decrease velocity. We don't need to know the mass of the object to calculate speed or velocity, distance or displacement, time, or acceleration in a kinematics problem. Now remember, you need to identify the numbers that you are given in order to find the number that you're trying to calculate. Let's begin to look at some real-world problems and begin to learn how to identify the physical quantities that are given in the example, as well as the physical quantities that we are trying to find. These are the physical quantities which you can find in the kinematics topic. Always look for these physical quantities in a problem first. Did they give you an amount of time? Did they give you a distance or a displacement? Did they give you a speed or a velocity? Now, if you're given a speed or a velocity, it might be the initial velocity, the velocity at the beginning. It might be a final velocity, the velocity at the end, or it might be an average velocity. You have to read carefully. The other thing that you might be given in a kinematics problem is an acceleration. Now, some givens are not in the problem as numbers. Some givens you figure out from the words. For example, if the problem says starts from rest or drops from rest, right? For example, if I take this ball and just let it drop, then the initial velocity of the ball was 0. So when you read in a problem starts from rest or drops from rest, you immediately write down that v initial is 0 meters per second. Right? So again, you have to be able to read to figure out numbers that you can't see. Similarly, you know if a problem says that an object comes to rest or stops, you know that the final velocity is 0. And you immediately write down v final equals 0 meters per second. Another thing you have to keep in mind when you're writing down numbers to complete a physics problem is you need to decide whether those numbers are going to be positive or negative. Now, the usual convention, any number that is to the east, to the right, north, up, or counterclockwise will be assigned a positive. Any number that is to the west, to the left, south, down, or clockwise will be negative. Now, remember, time and mass are never negative. Now, in this video, I'm going to keep the problems fairly simple. So that means that you're not going to have to worry about displacement south being negative or velocity west being negative, because when all of the directions are the same, we don't have to use positive and negative. It's not absolutely necessary. So in other words, if you have a problem and the initial velocity is negative, the displacement is negative, the acceleration is negative, and the final velocity are all negative, then you don't really have to put the negatives into the equations. So again, we're not going to worry about positive and negative in this video. Also keep in mind that time and mass are never, ever negative. Keep in mind there are many equations that are very useful, but they're not on your reference tables. One example is a second equation for average velocity. This equation is not on the reference tables. Average velocity is equal to the initial velocity plus the final velocity divided by 2. Now, the equation for average velocity that is listed on your reference tables, if you recall, average velocity is the total distance, right, divided by the total time. Right, technically this is average speed, but again, total distance divided by total time is going to get you an average. And taking two velocities and adding them together and dividing by 2, all right, we know how to take an average like that. Right, so again, keep in mind this equation for average velocity is not on your reference tables. And finally, you need to know what physical quantity you're being asked to calculate in the problem. Identify the physical quantity you are being asked to find with the correct unit and a question mark. So for example, if the question says, calculate the final velocity, or what is the final velocity of the dog, the truck, the airplane, V final equals, this is where you'll put the number when you get the final answer. Meters per second is the correct unit for final velocity, and there's your question mark. So you are trying to find, you know that you're trying to find the final velocity when you see the unit and the question mark. So here's our first problem. A mare named Sheba, now mare is a mommy horse, is running with a velocity of 2 meters per second south. Now again, the instant you come to a number that you can assign to a physical quantity, you put it right in. And since this is south, we're going to make it negative. So this is her initial velocity. This is the beginning. So V initial is negative 2 meters per second. All right, that's her initial velocity. She's trying to catch up to her little filly. A filly is a little baby girl horse, and the filly's name is Jessie. Over a distance of 20 meters in a straight line. Now she's heading south. And if you notice at the end, she's still going south. So that means that this displacement, all right, would be negative 20 meters. So we're going to put this in as a displacement of negative 20 meters. Now again, you can just say a distance of 20 meters, but since we know that she's going south, we can put down a displacement. We know she's going in a straight line, and we know also that her direction is not changing, because we see at the end here she's still heading south. All right. She accelerates to a velocity of 5 meters per second south. So her final velocity, when she gets done running faster, when she gets done accelerating, her final velocity is 5 meters per second still south. So that means V final is negative 5 meters per second. And the question, calculate the horse's acceleration. All right, so we're trying to figure out right here, acceleration, right, in meters per second squared, how much is it going to be? All right, and the other thing that we're trying to figure out in this question, how long did it take to catch up? How much time? So the other thing that we need to figure out for this problem is how much time. Now some problems will have one thing to figure out. Some problems will have 2 or 3 things to figure out. All right, now let's just make a note that we are trying to find acceleration. All right, we're trying to find acceleration, and we're trying to find the amount of time. All right, we're trying to find, oh, that's not going to fit up there. We're trying to find the acceleration and the amount of time. We probably won't need the average speed here, all right, but we'll worry about that some other time. All right, so what we've done is set up the problem. We know what we've been given, and we know what we're trying to find. Problem number 2. Citlali's motorcycle is parked on Elmont Road. She comes out of the restaurant with dinner and packs it in her saddlebags. She starts up her motorcycle. Okay, so now if the motorcycle is parked, then V initial must be 0. So we should put that right at the beginning. V initial is 0 meters per second. The motorcycle is starting from rest. She starts up her motorcycle and accelerates at a rate of 1 meter per second squared. All right, so the acceleration is 1.00 meters per second squared. Accelerates at a rate of 1 meter per second squared over a distance of 60 meters. All right, so the distance is 60.0 meters. Okay, straight north, so everything is positive. How long does it take to cover the 60 meters? All right, how long? How long we want to know the time. All right, to cover the 60 meters. What is her final velocity after 5 seconds? So V final, all right, we want to know here. We want to know V final after 5 minutes. 5 seconds. All right, and then we also want to know what is her final velocity after the full 10.95 second interval. So we want to know a second V final, all right, at 10.95 seconds. So we want to know, all right, how fast is she going at the end of 5 seconds, and then we want to know how fast she's going at the end of 10.95 seconds. Now I tell you what, let's move this over here for now. All right, we'll move this over here. All right, so we want to know her final velocity at the end of 5 seconds, and then we want to know her final velocity at the end of 10.95 seconds. All right, so we've got a couple of things that we have to find here. All right, we want to find the time probably first. All right, so we want to find the time, and we want to find the final velocity at 2 different times. Now, what you want to understand here is she's accelerating, so she's going faster and faster and faster. So there's a velocity at the end of 5 seconds. There's another velocity that's faster at the end of 10.95 seconds. All right, so you're going to have a velocity here. This velocity later is going to be faster. This will be a bigger number. All right, and we're trying to find this also. All right, so this is everything that we were given and everything that we're trying to find. All right, so let's list the givens for this problem, number 3. Marvell runs a total displacement of 80 meters in 10 seconds in a straight line east. Okay, so we've got 80 meters, all right, and it's east, so we know it's all positive. 80 meters, 10 seconds. And notice, I am not reading the entire problem and then starting. As soon as I get to a number, I get started. All right, or maybe I read 2 numbers. I cheated a little bit, but okay. If his initial velocity was 2 meters per second east, so V initial here, all right, is 2 meters per second. All right, if his initial velocity was 2 meters per second east, what was his final velocity? All right, so we're trying to figure out V final. That's going to be meters per second and a question mark. We're trying to figure out his final velocity. Now, obviously, he's accelerating. All right, his initial velocity was 2 meters per second east. He covered 80 meters in 10 seconds. All right, he's probably accelerating, so V final, right, is probably going to be higher. We'll figure it out. Now, calculate Marvell's acceleration using 3 different equations. Wow, okay, so they want us to do it 3 times just to practice using all the different equations. No big deal. All right, so we've got that. Okay, so we're trying to find his final velocity, all right, after traveling 80 meters in 10 seconds, and we're trying to figure out his acceleration. All right, so we're trying to find V final, and we're trying to find the acceleration. All right. We have here practice problem number 4, our last practice problem. In this problem, Giovanni drops a nickel from rest, so we know that V initial is 0. He drops it straight down into the Grand Canyon. At the same time, Sean throws a nickel straight down with an initial velocity of 4 meters per second. Now, first I'd like to briefly illustrate the difference between dropping and throwing. If Giovanni drops the nickel straight down, right, then he just lets it go, all right? So the initial velocity for Giovanni, the initial velocity of his nickel, all right, is 0. Now Sean throws the ball down. He throws it down fast. So the initial velocity for Sean is not 0, right? It's 4, and since he's throwing it down, his initial velocity is negative 4 meters per second. Now, let's take a look at the first 2 questions. The math will come in just a minute, and when we start the math, we will list the givens. Explain what happens to objects which are dropped or thrown down. Well, the same thing is going to happen to whether an object is just dropped or it's thrown down with some initial velocity that's not 0. In either case, the object is going to go faster and faster down. The Earth is going to cause the object to accelerate. It's going to cause the object to go faster and faster down. So you can write that as an explanation here. The objects will accelerate downward. The Earth causes the objects to go faster and faster down. You can also say the object's velocity increases as they fall. Now, second question, at what rate do objects accelerate? In other words, what's the number? What's the number for the Earth's acceleration due to gravity? At what rate do objects accelerate downward near the Earth's surface? Well, on your reference tables, and I'll put the answer up here, on your reference tables, it says 9.81 meters per second squared. Now, I'm going to round that up to 10 meters per second squared. And I'm also going to remind you that the Earth is pulling the objects downward. So this is a negative acceleration. Whether you use 9.8 or 10, this is a negative acceleration. So, practice problem number 4, our last problem. Giovanni drops a nickel. Well, if he drops it, then the initial velocity is 0. Okay? Drops a nickel from rest straight down into the Grand Canyon. At the same time, Sean throws a nickel straight down with an initial velocity of 4 meters per second. So he threw it down, so that's going to be an initial velocity of negative 4 meters per second. Okay? Now, what you want to keep in mind is that anything that is falling on its own near the Earth's surface is going to accelerate. The Earth is pulling it down faster and faster. So the Earth is going to cause it to accelerate at a rate of negative 10 meters per second squared. That goes for the nickel that Giovanni dropped and the nickel that Sean threw down. All right, so this is negative 10 meters per second squared. All right, so it's the Earth, the rate of acceleration is the same. And because the Earth is pulling the objects down, it's a negative acceleration. Okay, now, calculate how far down each nickel has fallen after 3 seconds. So Giovanni's nickel after 3 seconds and Sean's nickel after 3 seconds. Okay, now, how far down? So we want to know the displacement. All right, we know it's down, we know the direction, so we can call it a displacement. All right, here. And by the way, if we start up here and we end up down here, that displacement is technically negative. All right? Now, and also both final velocities at that time. So we want to know this final velocity at that time and this final velocity at that time. All right, so we want to know displacements and final velocities. We want to find displacements here. All right, find that. And we want to find final velocities right there. All right. So we have our givens, and we know what we're trying to find.